All right, welcome to our 3.1 notes. Let's get on with it and see what we've got. All right, we're looking at a table that compares speed and distance. The speed that your car is traveling and the distance in feet that it takes to stop. Can we verify if it's linear? Remember to check if it's linear, we look at the differences. This one is 46, and then 55, and then 65, and then 74, and then 84. So not linear, no. But you know what? If we look at the second difference, all right, this is 9, and then 10, and then 9, and then 10. It definitely is quadratic. All right, independent is our x, that's the speed, and our dependent is the distance. Okay, so let's plot all of this data. Notice that each square is worth 20. So my first point is 20, 63, and then 30, 109, and then 40, 164, 50, 229, and then 60, 303, and 70, 387. So those are the points. We also know that if you are going 0 miles an hour, it takes you 0 feet to stop. So we can plot those like that. All right. Now, if our police investigators wanted to measure the distance and then calculate speed, now our distance becomes the independent variable, and the speed becomes the dependent variable. All right, let's do the same graph. Let's switch our x and y. So now we're going to use our distance for x and our speed for y. And so we've got 63:20. We've got 109:30. We've got 164:40. We've got 229:50. We've got 303:60. And then 387 and 70. All right, so we've got those points, and we can connect them something like that. Now, for point of investigation, we are going to draw in y equals x on the graph. And remember, y equals x is just a diagonal line that begins at the origin and has x and y the same all the way through. So it looks something like that. That's my y equals x. All right. You may notice that if I took my paper and I folded it right along this line, and so that would all go down, that would wind up straight on top of the blue line. Okay? So this green is actually a line of reflection. Each point, if we measure perpendicular, each point is the same distance. Okay, so if I measure out perpendicular, I get the same distance each time I go. So this is what an inverse function looks like. We have just created an inverse function. An inverse function. The domain of a function is the inverse. The inverse of a function is a relationship in which the domain and range of a function are switched. The domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse. This is the scatter plot of speed versus distance, is the inverse of distance versus speed. So again, each of those are halfway away. If I were to fold along the green line, the red would go right on top of the blue. Okay? We can generate inverses graphically. A couple of methods that we can do. The first one involves identifying points. So let's pick some points on the graph where it hits the grid and label them. This is 3, 5. This is 2, 2. This is 1, -1, and 0, -4. All right? So all we're going to do is switch x, and y. Okay? So these points, 3, 5, 2, 2, 1, negative 1, and 0, negative 4 will just become 5, 3, 2, 2, negative 1, 1, and negative 4, 0. You can see I just switched the place of x and y. Now if I plot them, I get these points right here, like that. And I can connect the lines, la-di-da-di-da, there we go. And there's my inverse function. Visually, we can check it by sketching in y equals x, which would look like that. And we can see that it is y equals x goes right in the middle of it. Okay? Second approach we can use is we can first draw in y equals x. So first I'm going to draw in y equals x. Should look something like that. And then I'm going to identify points on the grid. There we go, there we go, there we go. And it doesn't really matter what the ordered pair of these points are in this method. I'm just going to check the diagonal distance. All right, so I'm going to go directly perpendicular to get the distance from each of the points, and then I'm going to go that much on the other side. So I can see for this first one right here, I have, it's 1 unit diagonally. So I'm going to go 1 more unit across and get to right there. This guy right here, you can see my little red dot, is 1, 2, and a half. So I'm going to go 1/2, and then 1.5, and then 2.5 to right there. And then this one is 1, 2, 3, 4. So again, going 4 across gets me right there. Now going the other way, this guy is halfway across. So going a full way across the box gets me there. This one is 2 full units to here, and then again right there. So now I can connect these points. And again, that shows me the inverse. My y equals x goes right in between them. And it looks like they're spun around or reflected across, if you will. All right. Last thing we'll talk about is the slope of these lines. What is the slope? So let's look at the slope of these functions. Okay, remember that slope is rise over run. Okay, so I can first notice that over here on my left graph, both slopes are positive. Okay, they're going up to the right and up to the right. So those are both positive slopes. So I can look, the red one is up 3 over 1, up 3 over 1, every case. The blue one goes up 1 over 3. So that's 1/3, both positive. On the other side, this one is going down to the right, and this one is also going down to the right. So those are both negative slopes. My red one goes down 2 over 1, so that's -2. The blue one is -1/2. Okay, so my slopes are 3 and 1/3, or -2 and 1/2, -1/2. Those, you should be able to recognize that those are reciprocals. And more importantly, they have the same sign. Okay, don't get confused by what we did in geometry in Algebra 1, where we found the opposite reciprocal to make a perpendicular line. These are inverse slopes, so they're just the reciprocal. Okay, next, if we wanted to get it into a table, this is very simple. Again, the principle of inverses is that we switch x and y. So all that we do is we take our y value and put it into the x. So this becomes -5. We take the x value and put it into the y, so that's 2. And we can do that the whole way through. And 7, 10, and 10, 12. All right. Same thing on the other side. This would be 9, -5, 7, -1, 5, 3, 3, 7, 1, 11, negative 1, 15. Okay. Last thing we'll say on this page, this notation right here, we say that as f inverse. So this function is the inverse of f. That negative 1 exponent means f inverse. All right, last of all today, we're going to talk about solving for these functions, getting the inverse algebraically. Okay, 3 steps. Step 1, write it as y equals instead of f of x equals. So my first step is I'm going to write my equation out as y equals instead of f of x equals. If it's already y equals, then you're golden there. Step 2 is switch x and y. That's the basic of what it means to be an inverse. I switch my x and y, all right? And then step 3 is all the rest where we solve for y. So let's see, I'm going to add 3 to both sides. Whatever I do to one side of the equation, I have to do to the other. All right, and then I'm going to divide by 2. So that gives me x plus 3 over 2 equals y. All right, we want to get these into an ax plus b format. So this is going to be 1 over 2x plus 3 over 2. That is my f inverse of x. All right. If that doesn't make sense to you, we can redo this step over here. Recall that dividing by 2 is the same thing as multiplying by 1/2. So that means I could have said x plus 3 equals 2y. So here I could multiply by 1/2 instead. The whole side by 1/2, and then I distribute. So I'm going to have 1/2 x plus 3 over 2 equals y. Okay, same thing as what I said my f of x was. Okay, for the next one, I'm going to rewrite it y equals 1/4 x plus 3. Switch x and y. And then solve for y. Minus 3. That gives me x minus 3 equals 1/4 y. To undo 1/4, we multiply times 4, which gives me, distributing the 4x minus 12 equals y. So g inverse of x equals 4x minus 12. All right, just a quick note as an aside, if we look at this in Desmos, you can see these are the two equations that we've talked about, 1/4 x plus 3 and 4x minus 12, and y equals x goes right in the middle of them. They're reflected, they intersect at a point that has the same x and y value, and they're crossing on y equals x, so that is a way to visually confirm the inverse. All right, next one works much the same. Y equals 3x plus 8. X equals 3y plus 8. Subtract 8 from both sides. That gives me x minus 8 equals 3y. Inverse of 3y is 1/3. So distribute that 1/3. That gives me 1/3 x minus 8 over 3 equals y. So h inverse of x equals 1/3 x minus 8 over 3. Last one, some of you may recognize that this is the temperature conversion. All right, so we can say this is our y equals 5/9 x plus 32. Switch x and y. X equals 5/9 y plus 32. And now we solve. Subtract 32 from both sides. So that gives me x minus 32 equals 5/9 times y. And I've got 5/9. So to undo that, I'm going to use the reciprocal. All right, so I'm going to say x minus 32 equals 5/9 y times 9/5. Multiply the whole side times 9/5. Cancels on the left, and I get y equals 9 over 5 times x minus 32 is the inverse. Or Celsius as a function of Fahrenheit equals 9 over 5 times F minus 32. There we go. That's usually the way we look at it. You could also say 9 over 5 F minus 288 over 5, but that fraction's pretty cumbersome. Thank you once again for tuning in for an episode of Coach Duhon's Notes. Sorry I missed a few days, but hopefully by next year when you read this, I won't have missed any days. So cheers, and let's have a great Unit 3. Bye now.